Swayam Prabha. Digital India. Educated India.
Here we had last class we had talked about the gives energy or the energy minimize. The criteria for spontaneous change is minimization of all the energy thermodynamic potentials, the energy terms, that means delta G, delta A, delta H and delta U, and maximization of the entropy for the system to continue to occur or for a process to continue to occur. So this we had derived in the last class. We are going to start with Maxwell's relations in this. Why is Maxwell's relation important? I think you are aware of it, at least in the first year you have done. The first Maxwell's relation gives you importance of the whatever thermodynamic parameter which we talk about, entropy, internal energy, in terms of certain measurable parameters, temperature, volume and pressure. So these are the equations which are most relevant. From here we are talking about the combination of the first law and second law. We are talking about equality sign, we are not putting in the inequality, and because we are talking about equilibrium states, we are not going to talk about spontaneity, we are talking about conditions when you have reached the equilibrium. So when you have reached the equilibrium, then we have the inequality replaced by the equality sign. So this is going to be the new term which we are going to have, delta U equal to T delta S minus PdV, and T delta S is coming from this Q being replaced by Q reversible. Okay, so this is that is nothing but T delta S. So this is the combination of the first law and second law. How the first law got modified, you see, the first law got modified by the change of the term dq. The amount of heat transferred between the system and surrounding, if it was carried out reversibly, then that can be equated with T delta S, because delta S is defined as dq reversible by T. So this is the new equation which we have for the internal energy. Now if we are having a closed system and non-PV work, we have not considered non-PV, only considered PV work so far, and we have always considered ideal system and a closed system. Now as I have developed one equation, we are going to develop 4 fundamental equations dealing with the 4 thermodynamic potential terms. So first is the internal energy, which we have got from the first law and second law, just replacing dq by T delta S. Now we have the definition of enthalpy, and you differentiate all throughout. Total differential, you can write down how the change in U plus P into change in V plus V into change in P. So this is how you can write down. Now you replace this with the value of delta U which you have calculated. Please do it. Please do it. I'm not going to read this out and how to do it. You please do it. Replace it and then we'll talk. Each time we are doing something, it is I am showing something in the screen. It is not working that way. You are supposed to do. So you replace this with this. What do you get? The PV will be cancelling off. So what you get a new equation for delta H. Delta H we had taken as delta U plus PdV. Now you are getting a new expression. The new equation of state is the new fundamental equations of the thermodynamic potential is delta H equal to T delta S plus VdP. Similarly, you have 2 more thermodynamic potentials, and you can rewrite from their definition. This is their definition, this is their definition, and this is the definition of A, the Helmholtz energy. U minus Ts, differentiate throughout. Differentiating throughout, you substitute the value of du, and you get the new equation, which is the fundamental equation in terms of the thermodynamic potential A. Similarly, you have from the definition of delta G, you have another equation of the thermodynamic potential G. So these are the four equations which we have of the four thermodynamic potentials or energy terms, and these are known as the four fundamental equations. Now, this is the term I was saying when we had discussed the entropy change. If you remember, I said how I can write delta S equal to nR ln V2 by V1 plus CV ln T2 by T1. I had told you how I can write this. This is, and some of you had said it is writing from the nRT PV equal to nRT equation. I said no, we are going to take it up when we are talking about the fundamental equations and Maxwell's. So have a look at this. Have a look at this from if you have this equation and you write down in terms of the CV, then the internal energy, this is one of the fundamental equations which we have just now derived. Replace this by NCV/dt, that is internal energy change, and leave the rest as it is, and divide throughout by T. What do you get? Divide throughout by T, what do you get? Take it to this side. So P by T into dV plus NCV dt by T. So if you want to find out the change, what do you have? You have this replaced by P by T replaced by NR, right? P by T replaced by NR, NR by V, sorry. So you can write down this is going to be a change in V2 by V1 and this is going to be a change in T2 by T1. Similarly, instead of enthalpy equation of the thermodynamic potential internal energy, you look into the enthalpy. What you can see, you write down the expression which you have derived just now and replace this by Cp and Ncp dt, and then divide throughout by temperature and find out what will be the entropy change from this expression. Here V by T you replace by NR by P and you get this expression. This expression we have already discussed when we were talking about entropy change. But here is how we derive it. It is not just from the first law, a gas law, but you have to come from the fundamental equations. I hope I'm able to clear your previous doubt here. Now, we are trying to define the thermodynamic set of new equations, the Maxwell's relations, based on four thermodynamic potential equations which we have here. Now have a look at this. This is the first, this is the second, this is the third, and this is the fourth. And all of these are state functions, right? All of these are state functions. So if these are state functions, then they can be written in terms of the total differential in terms of m being the first differential into dx plus the second differential into dy. Okay. So now let us look at this. When you say is a perfect differential, then when this differential with the respect to, this was differentiated with respect to what? This was differentiated with respect to M was differentiated with respect to, if Z was a function of X and Y, if Z was a function of X and Y, total change in Z was M dx plus N dx dy. What was M? Differentiating with which of the variables?
Delta X.
X. So differentiate with respect to X into total change in X. So if I have to have a parameter which is a perfect differential, then whatever is differentiated of X, M, will be now differentiated with respect to Y, keeping X constant. And if this was initially differentiated with respect to Y, now this has to be differentiated with respect to X, with Y keeping constant. And these two differentials, double differentials, should be equal. That was the criteria, right? That was the criteria for a perfect equation,
Yes, ma'am.
a perfect differential.
Yes, ma'am.
Okay. So if that is the condition, now have a look at this. Have a look at this. You have U, delta U equal to minus PdV plus delta S, T delta S, right? And U is a function of volume and say entropy. What is that? Is what we got from the new set of thermodynamic variables being dependent on thermodynamic potentials varying on various parameters. So instead of T, you can rewrite in terms of the S and V. So the total change in U is nothing but the change in U with respect to change in volume at constant entropy into total change in volume plus the total change in U with respect to entropy at constant volume into total change in S. Now compare this equation with this one, right? If you remember the Maxwells, sorry. So if you remember the Maxwells, relation, you have compare it with the fundamental equation of U, and according to that, if you compare this equation, this one with this one, then M is what? M is minus P. What is N? N is T, right? So if M is T, M is minus P and N is T, then what can we write? The double differentials as? What will be the double differentials? I don't know how many of you are with me. This I said is going to be the M. This is going to be the M, and that will be equal to minus P if I compare this. And this is going to be the N, and that should be equal to the T here in this expression. So if I do a double differential, what will happen? What will happen? The double differentials should be equal, right? So what is this? I have minus P, and that was what was that? Obtained after first differential with respect to P was entropy as constant. Now I have to differentiate this with respect to entropy keeping volume constant, right? So,
Yes, ma'am.
so I differentiate with respect to S with keeping volume constant. That's my double differential. And what will be the double differential from this side? It will be the differential of temperature with respect to volume, keeping entropy constant. And since the double differentials should be equal, because it's a state variable, so the change in temperature with respect to volume at constant entropy should be equal to the change in pressure with respect to entropy at constant volume with a negative sign, comes from the equation. Am I clear? So if you are done with
Yes,
this,
ma'am.
can you do it? Can you derive another one? Can you derive another one? Derive for this. I want somebody to tell me what will that be. Somebody do it and tell me. Aditi, are you there?
Yes, ma'am, I'm doing the second one.
Suprita?
Yes, ma'am, I'm doing it.
And what about Ipshita? Ipshita is there? I have not even checked your exam. Did Ipshita take the test? She had a problem at home. I did not get the time. How was the exam yesterday? Please give me the expression of the Maxwell's relation which we get from delta H, from the fundamental equation of delta H, which is nothing but change in volume into change in pressure plus T delta S.
Ma'am, it will be del V by del S at constant P equal to del T by del V at constant entropy.
Okay, so we have all these in one equation. Which was the equation which you got?
I got
Then
the uh,
del V by del
del
S.
at constant pressure.
Del V by del S at constant pressure will be equal to del
It's
T by del P at constant entropy. Did you get that?
ma'am, no, I
Yes,
got
ma'am.
yeah, yes, ma'am, yes, ma'am. That one.
What is
Ma'am, the
wrong?
seventh one. The
Yes, ma'am.
seventh equation you did.
It's the seventh
Yes,
one.
yes, and I hope you will be able to do it. So the partial differentials which you have, what does this signify? Suppose I read this. Suppose I read this. Delta G by T, this is coming from the equation this one, right? From this one we can say, according to the first differential of G will be equal to, that is with respect to temperature at constant volume, constant pressure will be equal to minus S. From this I can read this, right? What does that mean? What does that mean? It is equal to minus delta G by delta T at constant pressure is equal to minus S. What does that mean? That means if you are carrying out a process, that is, if you're carrying out a process in which you are suppose carrying out the process at constant pressure, and you are monitoring the change in G with the Gibbs free energy with temperature. And it gives free energy is a potential term. So the slope of G versus T, the slope of G versus, if I have the y-axis as G and x-axis is the independent variable temperature, then the plot between G and T will of that line of that condition or of that plot, the slope will be minus S. Okay, the slope of the line or the curve drawn between the variation of G with temperature for a given pressure will be nothing but the minus S of the slope of the plot, right? That means as we increase the temperature, the delta G should be decreasing at constant pressure because you have a negative sign. And what does the entropy mean? Entropy means whether it's a gas, liquid, or a solid. That will determine. So we'll take up that in a while. So you see the ones which is having the temperature and pressure relation with entropy. Okay, these are terms which are extremely important because it is going to be used in your evaluation or calculation work. So now I'm going to come down to the fundamental equation. See, the equation of state. Fundamental equations are four. These are the four potential thermodynamic potentials which we have got after the introduction of the second law, and these equations are four fundamental equations of the thermodynamic potential. Now, if you remember, we have equation of state. Equation of state for an ideal gas is PV equal to nRT. Similarly, we want to find out the equation of state for a system of a system which is other than what you have already learned, which is PV equal to nRT. So we can relate the temperature and enthalpy by a PVT data. So if I have a PVT data, I can be able to relate the temperature and enthalpy, or temperature and other internal energy also. So if I have whatever things which you can measure, we can measure is the temperature, we can measure the pressure, temperature, data can be obtained. We also can compute the value of delta H or H for a particular process. So which is the equation which we are going to take up? We have generated two equations. Now coming down to that equation, the equation of state, please remember this is, I don't know why it's not coming, the entire thing. The equation of state. Okay, now you can see the equation of state of what we have written. Have a look at this. I am trying to find an equation of state which is supposed to be a fundamental equation, and fundamental equation which we, if you remember, I had taken two terms which I had taken for ideal gas to be zero. What was that? Ideal gas, the fundamental equation of the form delta U versus change of delta U with volume at constant temperature was supposed to be zero, right? If you remember the
Yes, miss.
Joule's experiment.
Internal pressure. Internal
Internal
pressure. That
pressure. Internal pressure will be zero for an ideal gas. Now I relate that to the fundamental equation being generated in terms of T delta S by T into delta change in change in entropy with volume at constant temperature minus pressure. Now how can we write this? How can we write this in terms of measurable parameters, which is temperature, volume, and pressure? What is this? What is delta S by delta V at constant temperature? Do you have a Maxwell's relation for this? Have a look. Delta S by delta V at constant temperature. This one? That is what equal to
Yes,
the change in pressure with respect to temperature, and PVT is, we are trying to get the equation in terms of PVT. That will be only then we can say it's a equation of state, right? All equations in terms of the thermodynamic potentials being expressed in terms of PVT is how we get the equation of state, right? So we are trying to get down in terms of measurable PVTs. So this expression what we have, we now replace that with PVT, with this one, P delta P with respect to T at constant volume. This is what you are going to have. This can be further simplified. This can be further simplified if you remember the change of pressure with temperature at constant volume is nothing but the ratio of alpha by kappa, kappa T. So this is another equation you can develop. But what is more important is I have to show these are the two equations of state in terms of the thermodynamic potential U and H. H also we had taken H with respect to pressure at constant temperature was also taken to be 0 for an ideal gas. So let us show that if I do that in terms of the thermodynamic Maxwell's relation being used instead of the delta S by P form, then I should be able to show that for an ideal gas, this value will be, internal pressure will be 0, and this enthalpy change at constant pressure. What do we call this? This we called as internal pressure. What did we call this? We call this isothermal Joule-Thomson coefficient. There was a question yesterday on this.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So it is equal to minus mu Jt into Cp, right? For a non-ideal gas. So for ideal gas, this should be 0. So put in this equation. See, second one we have not derived. Second one, the second equation of state. Two equations of state we have found out, and both are in terms of the fundamental energy and thermodynamic potentials. One is U, one is H. So one expression is this one, and the other expression is T delta S by dP at constant temperature plus V. Now we have to replace delta S by P in terms of the Maxwell's relation. And if you replace that, you can write down in terms of volume with respect to temperature at constant pressure. So if you replace that and put in this equation, what do you see? Can you see that it's becoming 0? Can you show? You are finding out what is going to be change in pressure with temperature at constant volume. Use PV equal to nRT. Find out what is P. P is nothing but nRT by V, and differentiate that with respect to temperature at constant volume. That will be what? nR by V, right? nR by
Yes,
V, and nR by V is substitute that in this equation. In this equation, if you substitute, what do you get? P by T, P by T, and this T and this T will cancel off, and this T and this P is there, it is going to cancel off and give you 0. So for an ideal gas, it equals to 0. Similarly, when you take the other equation, enthalpy equation, enthalpy change with pressure at constant temperature equal to 0. So what will you do? Write down in terms of enthalpy with respect to pressure at constant temperature plus V equal can be further simplified if I replace this with the Maxwell's relation, and here we simplified in terms of the volume change with temperature at constant pressure. Find out what is volume. PV V equal to nRT by P. nRT by P, you differentiate with respect to temperature. What will happen? Now substitute that. It will come to V by T. Substitute that. T is going to cancel off. V minus V equal to 0. So you are proving it. For an ideal gas, if you have the equation of state, that will give you the energy thermodynamic potential with change in V, that is the internal pressure, and the value of isothermal Joule-Thomson coefficient values to be 0. That should be expected. Now let us prove that for a van der Waals gas. For a van der Waals gas, you write down the van der Waals equation. I can rewrite in the van der Waals equation in terms of P equal to RT by molar volume minus V minus A by the square of the molar volume. For that means it is all is per mole. So now you find out what will be the value of delta U by T. What will be the value of delta U by T? If you see, it is going to come A by square of the molar volume. Did you get it? Did you get it? A by square of the molar volume. And volume is non-zero, A is also non-zero, so it is not equal to 0 for a van der Waals gas, right? So are we coming back to the equations we had previously dealt with and assume something, and now we are in the state to prove it?
Yes, ma'am.
All of you got it?
Yes, ma'am.
Yes, ma'am.
Okay. So now I had said that I will not take up these equations, derivations of this equation in the class. But from the entropy equations, variation of entropy with temperature at various thermodynamic variables is supposed to be known to you so that you can simplify and go further. Suppose you are asked what is going to be the slope of entropy and temperature when the experiment is performed at constant volume. That is nothing but the slope is going to give you the measure of Cv by T. This. And how do you get it? How do you get it is from the fundamental equations. Fundamental equations is one is du and one is dh. From the fundamental equation, how you are going to get this? I leave this slide for a few minutes for you to understand. I'm not going to take up this any further. You have any question? You can come down and ask me right now. Because I'm not going to do these derivations in the class. This is absolutely boring and it makes no sense. This needs practice and you should do it. So I'm just trying to tell you, whenever I want to talk about the temperature variation of, we have talked about variation of the temperature terms U and H with various thermodynamic variables. Similarly, I can do that. We have done for volume also. We have done for pressure also, how they are changing, how volume is changing with pressure at constant temperature. This is also we have done. What I'm trying to say, that same thing can be done for a variation of entropy once you have done the Maxwell's relation. Once you have done the Maxwell's relation and you have the four set of fundamental equations, the fundamental equations you begin with, and this is the equation you begin with, and then you can find out what is going to be the change in U with temperature, because that's what you are trying to aim. And that from there you can, from the fundamental equation, you get a value in terms of the entropy change. And this entropy change should be able to be, we should be able to translate that value into something which is measurable. And if that is what is measurable, you can see if you use that from definition, you can find out delta S by delta T is actually given by Cv by T. So you don't need to measure this, but you can measure this. So these are measurable terms for which you can find out the values of the delta S by T, variation of delta S by T, delta S with T at constant volume. Have you gone through this? If I give you a derivation, you will be able to do it. These are the rest of the other equations which are there. Please take down the equations because it will take me some time to circulate the PDFs. I will take up G from the next class.